Good afternoon, everyone. Thank you for your attending. It is my pleasure to present another topic on the ISS steps imaging. First, as Dr. Weglein introduced, the Christian field data test has demonstrated the viability of the ISS steps imaging algorithm without a velocity model on a field data. Also, Professor Weglein mentioned that a practical challenge occurs due to the space-filling nature in multi-parameter ISS steps imaging formulated in terms of a combination of changes in acoustic elastic parameters, as we can see from this figure. And in order to avoid this challenge, a new concept is proposed to reformulate the algorithm in terms of migration result using a constant velocity. In this presentation, we will focus on the recent work we done on that reformulation. So this is the outline of this presentation. First, we are going to get an idea of how the ISS steps imaging work for a 1D acoustic Earth and normal incident plane wave, because this part has been previously covered by Professor Weglein. So we will quickly go through this part. And then I will proceed to present our recent work on the reformulation in terms of a constant velocity migration result. And then followed by an analytic example to illustrate and understand our reformulation. And in the end, there is a summary. So first, let's look at the ISS steps imaging for a 1D acoustic Earth and normal incident plane wave. So consider a layered acoustic medium with velocity profile C0, C1, and C0 with two interfaces at ZA and ZB. And we can, this is actual medium. We can choose a reference medium as a whole space with a reference velocity C0, and this is a perturbation. And then introduce parameter alpha to characterize this perturbation as using this equation, so we can plot the alpha as a function of depth, specifically to this layered acoustic medium, where we can see above the A and below the B, the alpha is 0, because above the A and below the B, the reference and the actual agrees. So this alpha is 0, but between the A and the B, there's a difference between the actual and the reference, so the alpha has some amplitude. Here, I would like to mention that where this amplitude, the amplitude of this alpha change indicates where the reflector is, and how much this amplitude change will give us the specific velocity change across the reflector. So where this amplitude change is an imaging problem, and how much this amplitude change is an inversion problem. So to solve for alpha by the inverse scattering series, we first expand the alpha in terms of different orders of data, where alpha 1, alpha 2, alpha 3 are linear estimates and quadratic estimate and cubic estimate of alpha. And then after this expansion in terms of the data, we can solve this alpha order by the set of inverse scattering equations. And so specifically, the D represents here the reflection data. If we are considering the imaging and the inversion problem, it will consist the reflection data consisting only primaries, where the reference wave goes and the multiple has been assumed removed prior to this step. And phi 0 is a normal incident plane wave, and G0 is the reference Green function, and K0 is omega over the reference velocity. So corresponding to our layered acoustic medium, we can use this first term in the inverse scattering theory to obtain a linear estimate of alpha as we shown here, and also as Professor Weglein just shown corresponding to this plot. So we can see these two primary with travel time T1 and T2 are converted using this reference velocity C0 at the ZA and ZB prime, because we use this reference velocity which agree with the actual above the first reflector. So this ZA is the correct depth, whereas this ZB prime is not agree with the actual step. So we add a prime on it. So this and R2 prime is T01, R2, and T10, whereas this R1 is the reflection coefficient for the first reflector. So then we can, then we use this data as input, and the first term, in the linear term of the ISS provides the linear estimate of alpha. And here we provide a plot of alpha as a function of depth, and here is a specific expression. And for comparison, we overlay on top of this alpha the actual perturbation. We can see this difference between alpha 1 and alpha in both amplitudes and where the amplitude change. Because here again we correctly located the first interface, so this is agree with the first interface is agree. So then taking the alpha 1 to alpha, it is a contribution from this nonlinear ISS terms. And here we would like to mention that so in calculating this alpha 2, alpha 3, etc., this quadratic and cubic contributions, the input is the alpha 1. For example, this alpha 1 to calculate alpha 2. And again, alpha 2 can be calculated in terms of alpha 1 and using alpha 1 to calculate alpha 3. So the input of this nonlinear calculation is alpha 1. And from this alpha 1 to alpha, it changes both the amplitude and the location of where the amplitude changes. So this involves both imaging and inversion work. We provide a expression for the second, the quadratic estimation of alpha in terms of alpha 1. And as Professor Weglein mentioned, there are two parts of this term. One is associated with inversion part, and one is associated with the imaging part. And if we, our focus is on the imaging only and keeps the amplitude the same, then we are only moving the box to its correct location, leaves the amplitude unchanged, as highlighted by this blue dashed line. So then we are only collecting the imaging terms contributions from each of these nonlinear terms. That will provide us the ISS depth imaging algorithm. In other words, we are collecting only the imaging contribution from these nonlinear terms, where it keeps this only moving the boundaries of the box, where it keeps the amplitude the same. So, so the key parts, as Professor Weglein explained, that the ISS imaging series in this specific 1D simple example is a cascaded series for this depth difference between ZB prime and ZB. And this depth difference is obtained using the input data directly and without any subsurface information. And this acoustic single parameter depth imaging is extended to multi-parameter depth imaging. And in this extension, a practical challenge occurs, as we mentioned in both Professor Weglein's introduction and in the beginning of this talk. To avoid this challenge, Professor Weglein proposed to reformulate the ISS depth imaging in terms of constant velocity migration results. As here we denote this constant velocity migration result using B sub 1. And our interest and our goal is correctly locating the reflectors that are mislocated in this constant velocity migration and keeps the amplitude unchanged. So we are only focusing on moving the mislocated images to its correct location while leaves the amplitude unchanged. To obtain the B1, the first term, from our experience and knowledge in developing the ISS internal multiple attenuation algorithm, we have a close relationship between alpha 1 and B1 in the K domain, as we show here. And because they have a such relationship in the K domain, and recall a property of Fourier transform, and in the depth domain, they have a simple relationship as a derivative. So as we expected, if alpha 1 is a box, then the B1 is a spike. So next, let me show you our recent work on the reformulation. Then to find B2, B3, and first following the definition of B1 and alpha 1, we define the Bn in terms of alpha n, where n is equal or greater than 2. And for example, to find B2, here we show these several major steps to how to find the B2 using the second order term in the inverse scattering series. We are not going to go through the details, but we refer you to our annual report for this detailed derivation. So following this second order term in the inverse scattering series and using the B1 as input, we can obtain an expression for as we highlight here in this red box. So next, I will show you a analytic example to explain and understand within the context of imaging and inversion to see what this term computes. So again, consider a layered medium that we considered earlier. And we have data due to a normal incident plane wave. We have two primaries with travel time T1 and T2 and the reflection coefficient R1 corresponding to the reflection coefficient of the first reflector, and R2 prime for the second primary, where it's corresponding to the two transmission coefficient and the reflection coefficient of the second reflector. And with this input data, and we can calculate the apply a constant velocity migration, we can obtain the B1, where the two events are converted at depths using this reference velocity here. So, and if we assume the C1 is greater than C0, then this ZB prime, it will be less, it will be smaller than its actual depth. So before I show you what this term specifically computes, let's remind ourselves what's our interest and what is our goal. If our interest and our goal is to move this mislocated events, this image to its correct location from ZB prime to ZB, and leaves the amplitude unchanged, if that's our goal, only focusing on move this location of this image and leave the amplitude unchanged, then let's imagine what has to do to achieve that goal. In particular, what has to do to achieve that goal in terms of the data. So as Professor Weglein introduced, what it has to do is to remove an image at this ZB prime and create an image at ZB. So then we can express this remove and creation in terms of the difference. And then we can apply a Taylor expansion of this difference. And then we can further expand the ZB prime and ZB. So this is an expression we finally get from this expansion. So here is a point. The same story happens here is we obtain this the difference between the actual and the mislocated depths in terms of the information we already know, because key here is this difference is directly expressed in terms of R1 and the information we know in the data, and it's only requires the reflections above the mislocated reflections. So then we have reviewed that our interest and what has to do to achieve that goal in terms of data. Then let's see what actually B2 computes. So we have two terms in the in B2. So as we mentioned earlier, our interest for the imaging is to move this mislocated image to its correct location while leave this amplitude unchanged. So let's first see what this first term computes. So given the B1, we can calculate this first term, which highlighted in red. This is the result we obtained. And if we compare these results with the expansion we obtain, we can see the results from this first part is exactly corresponding to this expansion of this first term. So from this analytic example, we know this first part is actually contributes to moving the image from this mislocated place to its correct place. Then let's look at what the second term contributes. So given this B1, and we can calculate the second term, highlighted here, and it provides the results as we shown here. So this is a very interesting result, and it communicates a lot from the inverse scattering series. So when we add these results from B2, particularly from this term, to this B1, we can see it alters the amplitude of the second image, not change the amplitude of the first image. So that's what that communicates from the inverse scattering theory is that there is no need to change for the first image. There is need to change for the second image. So then we think what's a difference between these two images that leads to the ISS communicates one need to change and the other one doesn't need to change. So we notice the difference between these two images that, so for the first image, its amplitude is 4R1. For the second image is 4R2 prime. This R2 prime is not R2 corresponding to the reflection coefficient of the second reflector. It's corrupted by this transmission coefficient. So what that communicates is when the ISS is formulated in terms of the migration results, it decides that it moves the reflector to the correct location corresponding to the contribution from this term, and it decides that it seeks to find the reflection coefficient of each reflection as the contribution from the second part. So because I do not need to change for the amplitude of this first image, so it needs the change of the second image. So that indicates this ISS, when formulated in terms of this migration, it seeks to find the reflection coefficient of each reflection, because right now, for the first term, it's 4R2 prime, which is corrupted by this 2 transmission coefficient. So this is different with the story when we formulated the ISS in terms of alpha 1. So when we formulated in terms of alpha 1, let's consider a single layered example as Professor Weglein also used. So we can consider a layered acoustic medium is C0 over C1, and the reference as C0. We have a reflection coefficient R, and define this perturbation. And we have a relationship between alpha and the reflection coefficient as we shown here. And what's the results, the calculation of alpha from the inverse scattering series is, so from the first, the linear estimate from the ISS is this. The quadratic estimation from the ISS is this term, calculate this term. First, for this problem, there is no imaging problem because we use this reference velocity agree with actual. So this term contribution is 0. There are no imaging problem. And however, this term gives the result minus 8R squared. And we can see this term and this term corresponding exactly the first 2 terms of this alpha expansion. So when the ISS is formulated in terms of alpha, it seeks to find alpha. However, when it's formulated in terms of the migration result, it decides to move the reflector to the correct location, this part, and find the reflection coefficient of each reflection. It's very interesting for us to see how the ISS, by this simple example, communicates to us what he actually wants to compute. So in the end, let's draw the summary. So this initial work is the beginning of the formulating the ISS depth imaging in terms of a constant velocity migration result to avoid the challenge occurred in the multi-parameter ISS depth imaging. And this work is just one step within a strategy to take the demonstrated viability to a toolbox option. And from this point, we will continue our work, and for sure we will benefit all the previous work of this ISS depth imaging. So with that, I would like to thank you for your attention. Thank you very much.